Alright guys, so this is our third and final video on the graphs of conic sections on the polar plane. And in this video we are going to talk about determining rectangular dimensions for our conic sections. And then we're going to graph those conic sections on the XY axis. So right here, what we mean when we say rectangular dimensions is of course the A, B, and C value that we used to define hyperbolas and ellipses on the XY axis. And on the way we're going to determine the eccentricity as well. So right here, given this form of a conic section defined by a polar equation, we actually don't have a lead one in the denominator, right? So our first step is going to be to determine the eccentricity by getting that lead one in the denominator. And the way we're going to do that is we're going to multiply by 1 over 10 over 1 over 10. And that's going to give us, right here, 18 over 10, or we could say 9 over 5 in the numerator. And then we have the lead one in the denominator when we multiply through by 1/10. And then we get plus, and we're going to say 4 over 5 sine theta. Right here, we've got the eccentricity of our conic section as 4/5, which is of course less than 1, which tells us that we're dealing with an ellipse right here. Now, we already know a lot about the conic section just by looking at the equation. Right here we can see that we have sine in the denominator of the polar equation defining our conic section, which means that we're going to be opening vertically. And then we can also see that there's an addition between the two terms in our denominator, which tells us that we're going to be opening vertically onto the negative y-axis. So right here, in general, what we can do is say that we're an ellipse opening vertically onto the negative y-axis. Then we know that the major axis of the ellipse is going to be between the r values that happen at the rotations of pi over 2 and 3/2 pi. So we can determine those r values. Right here, if we plug in pi over 2 into our original equation, we're going to get a sine value of 1, so that's going to be 10 plus 8 over dividing 18, so that's going to give us an r value of 1. And right here, if we plug in 3/2, we're going to get a sine value of negative 1, which is going to give us 10 minus 8 dividing 18, and 10 minus 8 is of course 2 divides 18 and gives us r equals 9. So at this point right here, what we can do is plot those points. We've got the r value of 1 for the rotation of pi over 2, and the r value of 9 for the rotation of 3/2 pi. Here we have our major axis, 2a, is going to be this length, which we can determine as 10. And right here, that gives us a equals 5. Now right here, if we know a equals 5, we can take the eccentricity, which we know can also be defined by c over a, and say that we've got 4 over 5 equals our c over 5. And that's going to give us the c value as 4. So now we've got the c and the a value, and of course the Pythagorean relation for our ellipse is going to give us our b value, the final value we're looking for. So right here we know that Pythagorean relation is a squared equals b squared plus c squared. And right here, plugging in our a and c, we get 25 equals b squared plus 16, which gives us a b value of 9. Not 9, but 3. B value of 3. So right here, we can now take those dimensions. We know that At the ends of our major axis are actually our vertices, and halfway between the vertices is going to be the center. So right here, for this length of 10, if we count down half that length of 5, that a value back to the center, we're going to get the ordered pair there of 0, negative 4 is the center. And now right here we can count out the minor axis, a length of b in either direction from the center. And right here we've got our ellipse. And we can even go as far as to plot the foci. We know one of them is going to be at the origin, right? That's 4 away from the center. And then right here, the other one is going to be at negative 8. And we can even come up with an equation for our ellipse right here. If we say that the center is going to be 0, negative 4, we've got our a value of 5, and we've got our b value of 3, so that gives us right here this vertically opening ellipse as y, and then plus 4 squared over, and then a squared is going to be 25 plus, and then x squared over, and then b squared is going to be 9 equals 1. And that defines the ellipse that we've just drawn right here. Okay, so right here, I'm going to let you guys give these next two a shot. With these next two, we're going to be looking to define the transverse axis for the hyperbola and the major axis for the ellipse. So right here, immediately it might be some use to go through and first get that lead one in the denominator and determine which of those we're going to be looking for here. If we go to this first one, we can say that if we multiply by 1/5 over 1/5, we are going to get 28.8 over 1, and then minus 13 over 5 cosine theta. So right here we can say that this guy is going to have an eccentricity of 13 over 5, which of course is greater than 1 and makes him a hyperbola. And we can see that for our last problem, if we multiply by 12, we'll let you guys do the last one on your own. Right, so the thing I wanted to point out was, right, for the hyperbola, we want to make sure that we're looking for the transverse axis. But I'm going to let you guys try the rest of these on your own, and we will come together and look at them in a second. All right, guys, so I thought we'd stop and look at the hyperbola, and then I'll let you guys go ahead and do the last one. So right here, for the hyperbola, of course, we know that we are opening horizontally onto the negative, or onto the positive x-axis, rather. But in general, right here, what we want to think is that in some ways it doesn't really matter. So as long as we know we're opening horizontally, that means that either the major axis or the transverse axis is going to be determined by the rotations of 0 and pi, right? So right here, we plug in 0 into our original equation, and we're going to get cosine of 0 is 1, so that's going to be 5 minus 13, giving us negative 8. And if we divide 144 by that, we get negative 18. So right here, for the rotation of 0, we're actually going in the opposite direction, 18, to define that vertices right there, that end of the transverse axis. And then right here, if we plug in pi, we're going to see 5 minus 13 cosine pi. Cosine pi is going to be negative 1. So right here, we get 5 minus 13 times negative 1, which is going to give us 144 divided by 18, which gives us 8. And of course, that's going to be this distance right here. So these two guys give us the transverse axis 2a as 10, which gives us a as 5. Then we can go over to the eccentricity and determine the c value as 13. Now right here, we know the Pythagorean relation for a hyperbola is going to be c squared equals a squared plus b squared. And right here, when we plug all that in, we get a b value of 12, which helps us to define the adjacent sides of our box. So right here, going halfway with our transverse axis, we can see that we've got a center of right here, negative 13, 0. And with that center of negative 13, 0, we can go ahead and go up 12 and down 12 from there, and basically get the dimensions of the box, then plot the diagonal asymptotes or the slant asymptotes through the corners of the box, and then we get the graph of our hyperbola from there. We could also come up with an equation for this guy. Right here we are we are going to be horizontally opening. So right here we can say that the equation is going to be x plus 13 squared. And then right here, we'll divide that by a squared, so that's going to be 25 minus, and then y squared over the b value squared, which is going to be 144 equals 1. And that would be the equation that defines our hyperbola. All right, so I'm going to pause the video now and let you guys give this last one a shot, and we'll come back and look at it together in a second. All right, guys, so here we are on the last one. We've got an eccentricity of 3/4 after multiplying by 1 over 12 to get that lead one in the denominator. That tells us that we've got an ellipse right here, and right here we know that this is a vertically orientated ellipse, so we're going to plug in rotations of pi over 2 and 3/2 pi. That gives us r values of 7 and 1, and when we plot those r values, we get the major axis extending from -1 to +7, and that gives us a major axis of length 8, which means that the a value is going to be 4. And right here, with the a value of 4, we can go back over to our eccentricity and say that we know that the eccentricity is c over a, so that means c over 4 equals 3 over 4, gives us a c value of 3. So we have to mention that the c value is not necessarily always going to be just the numerator of the eccentricity. It just happened to work out that way with these 3 examples. But right here we can go ahead and take that c value and use it to determine the b value with the Pythagorean relation for our ellipse. And right here, when we do that, we get b is the square root of 7, which is 2.6 approximately, and that's going to be the length that we go out from our center, which is, of course, halfway up the major axis, and basically we can say that would be, or the other way we can think about it is that it's a length a back towards the middle with from either vertices, right, that we've got right here and right here. But basically right here we get the graph of the ellipse there. Now if we wanted to get an equation for this ellipse, we could say with a center of 0, 3, the equation for this ellipse, vertically orientated, would be y, and then right here, -3 squared over, and then we would have the a value squared is 16, plus, and then right here, x squared over the b value squared, which would give us 7, and then that would equal 1. Okay, guys, so that's the last video. We will work on a worksheet tomorrow, and we'll work through some of this stuff then. All right, and I'll see you tomorrow in class.